Okay, in the name of Allah, the most compassionate and the most merciful. Afterward, by the permission, I want to start today my lecture, Measurement of Discharge. Today we will discuss how to measure discharge. There is many device or different types of device we can measure by that. And at the first time we will discuss about Venturimeter. What is Venturimeter and how is working and why is it's necessary for discharge. Venturimeter, it's a device used for measuring the rate of flow of a fluid flowing through a pipe. There is a components of a Venturimeter. It consists of three parts. Venturimeter has three parts or has three components. First, short conversion parts, short diversion parts. As you can see in the figure, maybe this figure is not very obviously, and you can see in the field or experimentally you can see in the laboratory or any place there is Venturimeter. It's you can see this is just only a simple figure of Venturimeter. You can see conversion parts, diversion parts, and throats. Here is differential manometer. Consider a venturi fitted in a horizontal pipe through which fluid is flowing. Just consider or focus on a Venturimeter fitted on a horizontal plane pipe that fluid is flowing through that. There is D1, P1, V1 and A1. What's this one? D1 diameter at inlet section 1, P1 pressure at section 1, V1 velocity of fluid at section 1, A1 area of section 1. These are the terms and it's similar like that. D2, P2, V2 and A2 corresponding value at section 2. This is you can see in the figure. D1, P1, A1 and V1 in the figure. We will, but how to prove that, how to prove and how to get an equation for this Venturimeter to do working very well. And we will applying by Bernoulli equation at section 1 and 2. We will apply from both sides, section 1 and section 2. Z1 plus V1 squared by 2G plus P1 by rho G. This is the general formula of Bernoulli equation. If we will applying for both sides, and we will write from to both sides Z1 and Z2, V2 square and V1 square by 2G plus rho plus P1 by rho G is from right side, P2 by rho G. Since the pipe is horizontal, when a pipe is horizontal, we don't have this distance from datum. It means Z1 and Z2 both are same. Same distance from datum line. They have same distance from that. But if Z1 and two both are same, but we can cancel out that v1 squared by 2g plus p1 by rho g is equal to v2 squared by 2g plus p2 by rho g. This is the formula, and we can change the side here and take common rho g from left side. We can take a common rho g p1 minus p2 from right side. We can take a common 2g, or we can, as you wish, or you want to take it common or not. That is depends on you. You want to take it common or not, but both are same. 2g, it's rho g. But here we can take from left side, rho g is common. And p1 minus p2 by rho g is equal to h. H is a difference of pressure. It's at section 1 and 2 pass. It's H is equal to F. H is equal to p1 minus p2 by rho g. We can substitute here the value of p1 minus p2 by rho g is equal to h. We can take a substitute. H is equal to v2 squared by 2g minus v1 squared by 2g. Applying continuity equation at section 1 and section 2. Continuity equation is a1 v1 is equal to a2 v2. We can we will find out v1. v1 is equal to a2 v2 by a1. Substitute this value to the equation. This h is equal to v2 squared by 2g minus v1 squared by 2g, and we can take it and substitute this. v1 is equal to a2 v2 by a1, and after substitute, h is equal to v2 squared by 2g into bracket 1 minus a2 squared by a1 squared. This is, we can take it a common a1 squared from lower side, and we will find h is equal to v2 squared by 2g into bracket a1 squared minus a2 squared by a1 squared into bracket. And if we want to find velocity or v2 squared, we can multiply from both sides, and we will find out v2 squared is equal to 2gh into a1 squared by a1 squared minus a2 squared, and we can take it from both sides roots, and squared by roots, it's cancel out from left side, right side is remaining, and a1 is cancel out by roots square, and v2 is equal to root 2gh into a1 by root 2 by roots a1 square minus a2 square. This is the last equation for velocity of this Venturimeter. And we have discharge. This is the very familiar and famous formula for discharge. Q is equal to a into v, and we have two sections here, a2 v2, and q is equal to a2. You can substitute from here. Instead of v2 we have value one equation that is already prove it, that a1 a2 into root 2gh by a1 square minus a2 square. This is the last formula for discharge of Venturimeter. This is very famous formula for that, and gives the discharge under ideal condition, and is known as theoretical discharge. Actual discharge, which is less than that theoretical discharge, and you'll find it theoretical discharge, and we can uh, take it if we want to find actual discharge. Actual discharge is less than theoretical discharge. Because of that, we can had one coefficient of discharge CD, and CD Q discharge of actual discharge is equal to CD into root 2GH into A1 into A2 by A1 square minus A2 square. This is the last formula for Venturimeter, and coefficient of discharge for Venturimeter is less than 1. It's something between 0.96 to 0.98. This is the derived equation for Venturimeter. Thank you for watching.